Hello everyone, it's Chemicator. Welcome back to another episode of Synthesis Studio. In this video, I'm gonna take a deep dive into the total synthesis of Laurenyene, represented by Boeckman in 2002. This target consists of a heterocyclic, unsaturated 8-membered ring with a chloro substituent at the 7th position. In addition, at the 8th position, an alkene is linked to a terminal alkyne. Another alkene is also installed at the 2nd position. All of these substituents are oriented out of the plane. This compound was first isolated from algae species widely distributed in tropical waters. Here you can see some of the secondary metabolites of these species. All of them have cyclic ethers of similar medium ring size. The key chemistry in the synthesis route is Enantioselective Reduction of ketones. The carbonyl group in ketones and aldehydes can be attacked from two faces. In other words, a nucleophilic hydride can approach from below or above the plane, resulting in racemic alcohols. When it comes to reducing ketones, lithium aluminum hydride and sodium borohydride are the most common reducing reagents, transferring hydride to the carbonyl groups. But stereoselectivity has always been a matter of concern. To this end, synthetic chemists design chiral versions of these reagents like vinyl modified lithium aluminum hydride and alpine borane. Bulky substituents in these reagents block one face of the carbonyl group in such a way that only the other face is attacked by the hydride. One of the more widely used solutions to this challenge is a chiral borohydride analog invented by Itsuno in Japan and developed by Kuri, Bakshi, and Shibata. It's based on a stable boron heterocycle made from an amino alcohol derived from proline, known as the CBS-catalyzed. Notice that the CBS-catalyzed is activated by treatment with borane, forming a complex. Once borane accepts the non-bonding electrons of the nitrogen atom, it becomes reactive enough that only a catalytic amount of the borane heterocycle is needed to reduce ketones. Now let's go to the 3D space to see what exactly happens when the active CBS complex approaches a ketone. Here we can see the chair-like transition state of this asymmetric reduction. There are two important interactions that make this reduction effective. In this part of the chair, borane becomes more reactive because it accepts the non-bonding electrons of the nitrogen. So the nitrogen atom acts as a base. On the other side of the chair, the oxygen of the carbonyl group forms a complex with the borane atom of the catalyst. In other words, the boron atom acts as a Lewis acid, making the carbonyl group more electrophilic. This is actually the beauty of catalyst design, combining a Lewis acid and a basic nitrogen, which significantly increases the effectiveness of the catalyst. Now let's focus on stereoselectivity. You know that bulky substituents tend to occupy the equatorial position. The reason is that in axial position, there is a serious 1,3 diaxial interaction, which destabilizes the structure. It's the same rule here. Notice that the best result in reduction with the CBS catalyst is achieved when two substituents on the carbonyl group have a remarkable difference in size. In this way, the bulky substituent prefers to adopt a pseudo-equatorial position. Otherwise, 1,3 interaction destabilizes the transition state. As a result, the hydride adds to only one face of the carbonyl group. The synthesis starts with this readily available diol. Then it undergoes a one-part double protection by selective methylation of the primary alcohol, followed by silylation of the secondary alcohol. After that, the sodium anion of diethylmalonate attacks the methylate via an SN2 type reaction. Then the diester acetal is unmasked by catalytic reduction to furnish the aldehyde. Now the stage is set for Wittig reaction. Treatment of this aldehyde with a stabilized yelate produces the corresponding enone. One side of this enantiomerically pure ketone is protected by PMB, which is a bulky group. Treatment with the CBS-catalyzed produces the corresponding alcohol with excellent diestereoselectivity. After deprotonation with pyridine, the allylic alcohol attacks 2,6-dimethylphenylchloroformate to provide the allylic carbonate. Notice that this hydrogen is acidic due to the existence of two withdrawing groups, so sodium hydride can abstract the acidic proton. Now this intermediate undergoes intramolecular cyclization, in which the carbonate moiety acts as a good leaving group. There are two options for ring closing. The nucleophilic carbon atom can attack directly at this carbon to produce a 6-membered ring, kicking off the carbonate. In addition, it can attack the allylic position. This is an example of the neighboring group effect, in which the double bond is attacked by the nucleophile and shifts its position. As a result, the carbonate leaves the molecule after the double bond shifts. Pause the video and rationalize which path is chosen. You might think that a 6-membered ring is more stable than a 4-membered ring, so it should be the major product. But that's not the case. Actually, the 4-membered ring is the major product. Let's take a look at the transition state to see what happens. As you can see, the sodium ion coordinates to both the carbonyl group of the carbonate and the oxygen of the enolate. So the two ends of the molecule are held tightly together. The result is that the nucleophilic carbon atom is placed closer to the double bond and can attack it more easily. In other words, in this particular example, sodium ion makes the formation of the 4-membered ring more favorable than the 6-membered ring. In the next step, this intermediate undergoes reduction by lithium aluminum hydride and then oxidation by Des-Martin protocol to produce the dialdehyde intermediate. This is because there is no reagent for direct conversion of an ester to an aldehyde. Look at this intermediate. There are two double bonds linked by 3 single bonds, so it's prone to a free sigmatropic rearrangement to create the 8-membered ring. Releasing the strain energy of the 4-membered ring is a driving force of its rearrangement. If you wanna see a beautiful application of sigmatropic rearrangement, check out this video. This 8-membered ring includes two double bonds. One of them is reduced in the next step. So we need a reagent that can differentiate between the two double bonds. Wilkinson's catalyst gives us this kind of selectivity. Pause the video and think about which double bond is reduced. Wilkinson's catalyst reduces the less hindered alkene. As you can see, this double bond is more hindered than the other. Moreover, it's more stabilized due to conjugation with the aldehyde. After selective reduction, this intermediate undergoes decarbonylation. Again, a catalyst based on rhodium is used in this reaction. The diphenylphosphonopropane ligand reacts with the pre-catalyst to create a cationic species which is more reactive than the Wilkinson's catalyst used in the previous step. Mechanistically, the active catalyst inserts into the carbon-hydrogen bond during oxidative addition. After that, it undergoes retro-CO insertion. Finally, the carbonulated product leaves the molecule during reductive elimination. The catalyst can lose the CO to regenerate the initial active species. If you have any trouble with oxidative addition or reductive elimination steps, check out this video to deeply understand the application of transition methods in organic synthesis. In the next step, an epoxide ring is introduced to the double bond by DMDO. Because of the specific architecture of the substrate, the epoxide ring is formed below the plane opposite to the substituents. Next, a hemiacetal is installed on the molecule. N N-dimethylhydrazone is used for this transformation. Firstly, LEA abstracts this proton. Subsequently, the nitrogen accepts the electrons and becomes a negatively charged species. Now it acts as a good carbon nucleophile which attacks the epoxide ring via an SN2 reaction, opening it up. Notice that this stereocenter is inverted during the reaction. Now the negatively charged oxygen attacks the imine bond to create a 5-mer ring. Hemiacetal is obtained after hydrolysis. In the next step, the N moiety is installed on the molecule. To this end, butyl lithium abstracts the hydrogen of the hemiacetal, leading to the formation of the alcohol and the aldehyde. Next, the aldehyde is converted to alkene by Wittig olefination. Notice that the end of the alkyne is protected by TMS. After that, the alcohol is oxidized by Des-Martin protocol. Now it's time to install the alkene moiety on the ring. So the alcohol is deprotected by DDQ, which is a standard reagent for deprotecting paramethoxybenzyl group. In this way, the other protecting group remains untouched. The resulting alcohol is then oxidized by Des-Martin protocol to produce the corresponding aldehyde, which is then converted to an E-alkene by Takai Olefination. The mechanism of this type of olefination is not well understood. In one of the proposed pathways, a geminal diiodide reacts with CrCl2 to produce a geminal chromium species. Nucleophilic attack of this intermediate on the aldehyde leads to the beta-oxy-chromium species. In a Newman projection, you can see the R group and the methyl group adopts an anti-conformation. A formal elimination then leads to the alkene with the methyl substituent in the E configuration. Next, HF is used to deprotect the alcohol. After that, methylation converts it into a good living group, setting the stage for the elimination step. Notice that there are 2 alpha hydrogens that can react with the base. Elimination of this particular hydrogen leads to the conjugated product, but that's not the desired product. So choosing the right base is crucial in this step. DBU is a large and non-nucleophilic base that prevents the formation of the thermodynamic product. In the next step, the carbonyl group undergoes stereoselective reduction by the CBS-catalyzed to produce the alcohol. After that, chlorine is introduced to the molecule by the Appel reaction, along with inversion of stereochemistry. Finally, the terminal alkyne is smoothly liberated from the molecule under basic condition.